All right, this is chapter 10 for Physics 151, beginning with question 4. Question 4 reads, the Coulomb force can be extremely strong compared to gravity and can act over very large distances. Why then is the orbit of the moon around the Earth determined by gravity and not by electric forces? So, if we consider the Earth and the moon, not to scale, they are bound only by gravitational forces. But if the charges of the Earth or the Moon were not negligible, that is, the net charge of the Earth or Moon were not negligible, then the electric force would very much be a considerable force to deal with. But because on the Earth we have positive charges, and then we also have negative charges, so that the net charge of the Earth is basically neutral. And then that's also true with the Moon, that the Moon has positive charges on it and negative charges, and so that the net charge of the moon is neutral. That means that the electric force between them is basically zero. Right, so question 6. How are electric potential energy and gravitational potential energy similar, and how are they different? They are very similar in the sense that if I have the Earth and I have an object and I move it within the Earth's gravitational field, then I have given it gravitational potential energy. Remember, we calculated this. PE is mgh. All right. And that's due to moving the mass within the gravitational field of the Earth. And if I lift the mass a certain distance from the surface of the Earth, then it has more potential for motion. Right, that is potential energy. It has potential for motion. In a similar way, let's say that I have a positive particle here, and I move a charged particle within the charged particle's magnetic field, then I give it also potential for motion. So let's say, for example, I have another positive particle, and this is one of the ways that it's different, and I move it in this direction. I have increased its potential energy because as I move it closer to that positive charge, it feels a bigger force. So if I were to label the electric forces here, it would look like that, and here the force would be much bigger. So here, this positive particle would have more potential energy because I now have a greater force, a greater electric force acting upon it, and so it has more potential for motion. All right, so question number 9. Okay, so we'll go back to question number 6 to make sure we're clear. They're similar in that they both depend upon the position of either the mass or the charge dependent upon within the field, either the gravitational field or the electric field of the mass or the charge. So that's how they're similar, in that they're dependent upon the position of the electric field or the position of the mass or charge within the field, whether it be a gravitational field or an electric field. And remember, the field just describes the force either due to the mass, in the case of the gravitational field, or the charge in the case of the electric field. They're different in how we can increase the potential energy. All right, so for example, with this, I increase my gravitational potential energy by moving it up. And then if I let it go, it's going to fall and increase in motion. All right. With the charged particles, it's a little more complicated because you have to consider the charge. Right. So if I have two positive charges and I move them really close together, then I've increased the potential for motion, because if I let them go, they're going to fly apart with very large forces. Right. If I have two negative particles, if I move those close together, they're also going to have great potential energy because the forces are a lot bigger and they will have a greater potential for motion, All right, so they're slightly different in their potential, the position dependence, that is where I have greater potential energy. All right, so let's see, question number 9. Explain how atoms in a substance at high temperature might lose electrons, as happens in the filament of a CRT. Further, why would electrons be freed from their atoms at higher temperatures than at lower temperatures? I have these electric forces. So I have a positive nucleus, and then I have these electrons that go around this nucleus. And these electrons are bound by the electric force. But if I increase the temperature of these atoms, those electrons will be moving at a very fast rate because of the increase in temperature. So they are ejected when the temperature increases because the thermal energy exceeds the electric energy. And if you increase them to a high enough temperature, then the motion of those atoms will cause the thermal energy put into those atoms will cause those electrons to be ejected, which doesn't happen at lower temperatures. All right, question 10. Consider the vertical steering plates in the CRT in figure 10.5. Let's see, that's on page 269. The vertical steering plates, they look like this. I'm just going to draw the vertical steering plates. You have these two plates and a beam of electrons travels through those plates. And then those vertical steering plates will create an electric field that cause the beam of electrons to either go up or down. In a CRT, you have this screen, and these electrons can either go in this direction or they can go in that direction, and the vertical steering plates are used to direct the beam of electrons to the back of the screen, and wherever they strike, it will produce a certain color. If the voltage is applied to those plates, steer the beam of electrons upward, should the upper plate be positive or negative related to the lower plate? All right, so I want to know what will cause them to move upward like this. I want to direct this beam of electrons upward. That means that I'm going to have positive plates here and negative plates here. Remember, negative charges repel, like charges repel, opposite charges attract. So these negative charges, as they go through these two plates, they will be repelled from the negative charges here and attracted to the positive charges here, which will cause a force upward, causing the beam of electrons to go upward. That's question 10. Let's move on to the problems. How many excess electrons does an object with a total charge of -1 times 10 to the minus 9 coulombs have? So I have this total charge of -1 times 10 to the minus 9 coulombs. Notice that it's negative, so these must be electrons. And the charge of one electron is equal to the fundamental unit of charge. One electron is equal to 1.6 times 10 to the minus 19 coulombs. So if I want to know how many electrons are in this charge, I just divide it by the fundamental unit of charge. Like this. And that'll tell me the number of electrons that's in that charge. So 1 is 10 to the minus 9 divided by 1.6 times 10 to the minus 19. I get 6.25 times 10 to the 9. That's 6250. Write it out longhand. 6.25 times 10 to the minus 9. So that's what? 6,250,000,000 electrons. And it says that's roughly the amount of charge involved in commonly encountered static electricity. So for example, when you touch your car and you get shocked a little bit on your finger, you're transferring over 6 billion electrons from your body to the car, or vice versa, from the car to your body. Problem 3. Calculate the force between two identical charges separated by 1 centimeter. So my charges have a magnitude of 1 times 10 to the minus 9 coulombs, and they're separated by a distance r of 1 centimeter. I'm going to convert this to meters. That's 0.01 meters. What is the force between these? From Coulomb's law, F is equal to K Q over R squared. K is Coulomb's constant. That's on your equation sheet. 9 times 10 to the 9th Newton meter squared per Coulomb squared. Times my two charges. That's 1 times 10 to the minus 9. 1 times 10 to the minus 9. Divided by the distance squared, 0.01 squared. These are both in coulombs. And so that force is 9 times 10 to the minus 5 newtons. All right, so this is also the amount of charge that's involved in static electricity. So these 6 billion electrons feel a force of 9 times 10 to the minus 5 newtons. That's 0.00009 newtons. So it also asks, what is the force if the separation is doubled? So if I double this separation, I'm just going to say it's twice that. Don't forget to include the squared there. 2 times 0.01 squared. You get 2.25 times 10 to the minus 5. So if I double the separation, I get 2.25 times 10 to the minus 5 newtons. But notice, though, that if I increase R by a factor of 2, that means that I have to make it the same. I have to have a 1/4 over here, because 2 squared is 4. So I could just multiply this number times 1/4, and I'd get the same thing, 2.25 times 10 to the minus 5. And if it's tripled, I would take 1/9 of that. I'm going to sort of draw it up here. Let me make another space. So tripled, I'm just going to say it's 1/9 of the original force. That's 0.00009 divided by 9, which is 0.001 newtons. All right, because if I triple R, that means my force is decreased by a factor of 1/9. What if the force if the charges are increased by a factor of 10 and the separation is kept? All right, so if I increase these charges by a factor of 10, I have a factor of 10 on both Q's. That means that I'm going to increase, this is part C, I'm going to increase my force by a factor of 10 squared, which is 100 times F, which is going to be 0.0009. I moved that decimal place over 2 places. 0.009 newtons. It's very useful to be able to deal with relationships in this way. If I change one variable, what happens to the other variable? If I multiply the charges by a factor of 10, then I get a factor of 100 for the force. If I multiply the distance by a factor of 2, for example, that's 2 squared, so it decreases the force by a factor of 4, 1/4. You'd very likely see questions like this where I ask you, what happens if you double the distance? What happens if you double the charge? Those sorts of questions, these sort of mathematical relationships. Not numerical problems necessarily, but just mathematical relationships. All right, problem 5. Calculate how far apart two identical charges of 1 coulomb must be in order for the Coulomb force to be 500 newtons. All right, so I have charges Q equal to 1 coulomb, and the force is 500 newtons. And I just want to know how far apart must these charges be in order to give that force. A coulomb is a really big amount of charge. Usually when we talk about charges, we talk about them in terms of microcoulombs or nanocoulombs. Uh, so we're going to posit then that in order to get this force, these two charges, well, let's just look at it. So F is equal to K QQ over R squared. If I want to solve for R, I'm going to multiply both sides by R squared and divide both sides by F. And so that means that R squared is going to be KQQ over F. And then I want to take the square root of both sides. So R that's the square root of 9 times 10 to the ninth. Say Q is 1 coulomb over the force, which is 500. So it's going to give us our distance. It's 9 times 10 to the ninth. $4,200 meters. .2 kilometers. Really big charges. To get this force, you have to put them really far apart, right? Because these are very large charges. All right, problem 5. Let's see, problem 7. The energy expended by a battery is related to both battery voltage and the amount of charge it moves. Calculate the energy in joules put out by a 9-volt calculator battery that moves 3 coulombs of charge through a handheld calculator after 1 hour of operation. Potential, electric potential, this is different from potential energy, but related, is equal to the energy per unit charge. Potential is the energy per unit charge. So it's related to the potential energy, but it's a potential energy per charge. So how much potential energy does each charge have? We would say this is V is, I'll call this potential energy over Q. So for problem number 7, my voltage, or my potential, we commonly call this voltage, electric potential, is 9 volts, and it's equal to the potential energy over the amount of charge that it moves, 3.0 coulombs. So my potential energy, if I multiply both sides by 3, is equal to 27 joules. The 1 hour is irrelevant. If I wanted to know the amount of power, by the way, we've seen power before, I would just say 27 joules, the amount of energy, divided by the amount of time. 1 hour is 3,600 seconds. And I can find the wattage, or the power, is 27 divided by 3,600. 7.0075 watts. Calculator is a very low power device. Right. In part B, it says calculate the energy put out by a 12-volt car battery that moves 1,000 coulombs of charge. Right. 12 volts moves 1,000 coulombs of charge. It takes an enormous amount of energy to start your car. All right. Just to get it started, you have to get that whole engine moving. So if I want to know my energy, voltage is potential energy over charge. So that's 12 is equal to potential energy over 1,000. 12,000 joules. You know, we can get an idea of the power. Let's say we estimate the time to start your car. Let's say, I don't know, 2 seconds. That you're actually engaging the starter motor, 2 seconds to start your car. Then we can get a feel for the power. And, you know, keep in mind that like your hair dryer, which is probably one of the most energy consuming devices in your house, the highest power rating, it has a power rating of about 2,000 watts. All right, but this has a power rating, roughly, sort of estimating 12,000 joules, divided by about 2 seconds, 6,000 watts it's pulling. All right, that's problem number 7. Problem number 9. Calculate the speed of an electron accelerated by a voltage of 12,000 volts. Write that down. Voltage is 12,000 volts. Remember, when I say voltage, I'm also saying potential. That is the amount of energy per charge. So anytime you see voltage or a unit of volts, think energy per charge. I want to know the speed of an electron. So I know a few things about an electron. I know the charge of an electron is 1.6 times 10 to the minus 19 coulombs. I also know the mass of an electron. You don't need to know this number, it's on your equation sheet, but it's 9.11 times 10 to the minus 31 kilograms. All right. I want to know, what is its velocity? What is its speed? When you see this, you should think, kinetic energy. When I put this electron through a certain potential of 12,000 volts, it gains energy. And that potential energy is converted into kinetic energy because it begins to move. And I want to figure out how much energy it has, and then I can find the speed. So I can first find the energy. I say V is the energy per unit charge. So energy is equal to V times Q. That's 12,000 times 1.6 times 10 to the minus 19. I can leave the negative off here because that's really going to deal with the direction that it's going. And I'm not really concerned with the direction. I only want to know the magnitude. So 12,000 get 1.92 times 10 to the minus 15 volt, or joules rather, that's an energy. And then this energy is the kinetic energy, which is 1/2 mv squared. 1.92 times 10 to the minus 15 is equal to 1/2 I'm going to divide both sides by 1/2. Then I'm going to square root both sides. These things will cancel, and that'll give me V. So that's 6.5 times 10 to the 7. So when I accelerate this electron across these 12,000 volts, they pick up a speed of 6.5 times 10 to the 7 meters per second. 650 million meters per second. No, 65 million meters per second. Excuse me. 65 million meters per second. All right, problem number 9, last one, problem 10. Coulomb forces can be used to attract charged paint droplets to an object. This is like in an inkjet printer, for example. This method is sometimes used to apply paint or felt to odd-shaped objects. Calculate the speed of a 1 times 10 to the minus 3 gram droplet. So the mass is 1 times 10 to the minus 3 grams. Just before it strikes an object, if its charge is, the charge of this object is -1, and then there is a 500 volt potential difference between the object and the droplet starts from rest. This is very similar to the previous problem. It's basically the same. I first find the energy from these two values. That's the energy that the paint droplet gains. The energy is equal to Q times V. And that's going to be 500 times 1 times 10 to the minus 15. It's 5 times 10 to the minus 13. So that's the energy that the paint droplet gains, that number of joules. And then if I want to know, and then that's also going to be equal to its kinetic energy. And kinetic energy is 1/2 mv squared. This is on your equation sheet. It's on a previous chapter, these energy and power and all that jazz. I want to know the velocity. See, I'll write it out longhand. So it's 5 times 10 to the minus 13. Actually, we need to convert this into kilograms. So this is 1 times 10 to the minus 6 kilograms. On the quiz, I'll have them all the correct units already. Times v squared. Just like we did on the previous, math is the same. These cancel, and it gives me v. One times 10 to the minus 3 meters per second. So in contrast, this paint droplet, which has a fairly large mass in comparison to the charge in the previous problem, it has a fairly slow velocity as it's being accelerated onto this object, like in an inkjet printer, or in this case, this is painting some object, but it's similar in an inkjet printer. I think that's the end.